Hey class, welcome back. So this is a follow-up video where we're looking at procedures, functions in ARM assembler. And we're going to go deeper into that. And we're going to talk a lot about stack memory in this video. A topic that you probably haven't thought about in a while, but it's exceptionally important, and we're going to see it from a different angle. All right. In the past, you're thinking of stack memory in the context of dealing with higher level languages such as C, and thinking of it from that perspective. But now we're going to look at it from a little bit more of a lower level perspective of what's happening. All right, and the program counter is a big part of that. Okay. So as an example, we'll keep the example fairly simple in the video because we can follow up with more complicated examples directly and together in class. Let's look at an example if we're trying to implement a square function. All right, all we want to do is something along the lines of this. This is an example in C where we're trying to have a function that's just performing the square of some input, okay, and returning it. Very simple, okay. In main, we're calling the function, we're going to call this is the caller, right? We got the function call, right? And then the function itself that's being called, that's the call E, okay. And then we want to remember, we started hinting at this towards the end of the last video, that if we're calling a square function, what we really want, right, is that we can pass in our input. In this case, we'll call it n1. We want to pass in our input into the square function, okay? And then we want to be able to send out our output, okay? In here, we can call it num or x, right, whatever the return is. And we don't want the caller should be very independent of the call E, right? As we've seen always in C and other languages, is these are in different scopes. Okay, we shouldn't have it such that variables collide in different scopes. Okay, so if as an example, if I had called this down here num, and then returned num, right? We know that in higher level languages, the num here is a different variable than the num here because they're in different scopes. And we want that principle to hold true from an assembly language perspective. Okay. Now, in a previous video, that was not really the case because we looked at the isEven function, and we had when we looked at the implementation of that function, we had all sorts of registers being used that were that could collide outside of that function. So we could have registers being used in the callee that would impact the caller and vice versa, right? That they were really, the registers are all in one kind of scope. We hadn't looked at any way of keeping things separate, okay? And that's a problem. That's a big problem. It breaks one of the big rules in terms of computing. Okay. Now what we're going to do is we're going to specify some conventions. This is these conventions are typical, okay? And we're going to look at our registers, and we're going to define some registers as temporary registers, okay? And that means that they do not need to be preserved across a function call, right? The way to think about that is if it's a temporary register, is if you're inside of a function, you have any right to go ahead and overwrite that data without being worried about preserving it or backing it up, okay? However, we're going to have other pieces of data, such as saved registers, right? Where if we use those inside of a function, we're going to have to do something where, like, imagine we're using register 9, okay? If we want to use that inside of our function, we're responsible to back it up in memory, then we could use it however we see fit. And then when we're done using it, we need to restore it. We need to restore the original. Okay. So effectively what we're doing, we have a very small number of registers. Okay. Inside of our function, we need to use registers to do the work. Okay. And we have certain registers that have some conventions on them such that if we can use them, right? But if we do, we need to back up the original piece of information. Okay. Then we can use it for whatever we want, right? And then we just need to restore it when we're done, okay? So you can kind of think of it as like an example of like if you were going to go ahead and, if you're borrowing money from a friend or something, you can take that $100, right? You can go ahead and use it however you want, right? But when you're all said and done, you need to get that $100 back and return it to the friend, right? It's kind of the same idea. This way, the friend doesn't necessarily care; they're getting their money back. You just borrowed it for a period of time. That's kind of the same idea with any of these registers that are preserved across a function call. We can use them inside of a function however we want. We just need to back up the original in memory, right? Use it however we want, and then return it. Okay. If it's a temporary register, we could just overwrite it. We don't care, right? It says, hey, that's the example of almost like you're leaving money on the ground, or if there's something there, right? Somebody's not using those registers correctly if they're expecting the data to be there as soon as a function's called, right? The moment a function's called, anything in temporary registers you have to assume is no longer valid data. Okay. Now we'll do examples of this. I'm going to keep the example in this video very short and very simple, right? We want to kind of build to more complicated examples at a later time. So let's look at, to build this square root function, let's keep in mind that it actually is using a multiplication operation here. We have yet to see how to do that. I've already built it here in assembler. And I don't care how, we're not going to go and trace through this. Effectively what this is doing is, there's multiple ways you could build this. The one I'm showing is a more complicated than it needs to be, but is effectively doing a bitwise manipulation to calculate the multiplication. You don't need to do it that way. There's other ways to do it. This is a little bit more similar to how the underlying hardware does it, but that's besides the point. All right. So effectively, this is passing in we don't really care about. The point here is we don't care about the implementation details, right? Somebody who writes a function, right, should build it in such a way that somebody can use it without caring about how it's built, right? All they care about is how to use it. What do they need to pass in, and what's the result, right? So here they need to pass in the two parameters in R0 and R1, and the result's going to get saved in R3. That's the only thing somebody using this function needs to be aware of, okay? So before we do the square root function, which is really just a special case of this, let's take a look at these registers in here. Okay, and notice that the only registers I'm using in here are the input, R0, right, and R1. I'm also putting the result in R3. Every other register, the highest register I'm using is R8. Right? I point that out because if we come back over here, right, all of those are temporary registers. All of them are temporary except for the ones that are our input arguments or result registers 0 through 3. All of these do not need to be preserved across a function call. I don't need to back them up. Okay. However, the return address is preserved across a function call, and I am using that, right? I am using that because the moment this function gets called, right? If we call the multiplication function up here, the moment that gets called, we're overriding the return address. Okay. So to properly build this function, I should do the following. I'm going to back up, right? I should back up the return address. And I'm going to do that by saving it on the stack. SP, this register here, stands for stack pointer. And what I'm doing is the stack pointer starts at a high address. I'm going to subtract 4 bytes. I'm going to make room 4 bytes. I'm going to subtract 4 bytes. And I'm going to save that return address on the stack. Okay. And when I'm done, and I no longer I've saved it, and it's backed up, I can go ahead and return it here. Okay. Now, this is a little bit overkill here because this is sometimes referred to as a leaf function. There's no function calls inside here. So you can actually kind of get away with not doing this in this one case, but I'm going to show it as an example anyway. I'm going to store it. I'm going to store the return address, okay, in that new stack location. Okay. So this is, as you've seen with stack memory before, this is a push onto the stack. Okay. And then before the program ends here, I'm going to pop from the stack. I'm going to return it. And I'm going to set the stack pointer back to what it was. Okay. Now, like I said, this one is kind of considered a leaf function because it's not actually having another function call in here. So I actually don't need to do this in this case for this one, but I'll show you in a moment where it does matter. All right. But effectively what we're doing, right, we want to remember what we're doing, is it went and made room on the stack for that return address and then returned it when it was all said and done. Now that might not matter for this one because there's no function call in here, but if we didn't do that for the square, right? So here I'm going to try to take 5 squared and I'm going to implement this function here. I better do something similar here. This one it's required, right? Because if I don't, right here I'm doing a branch and link where I'm going to call the multiplication function. Right before I call that, right, so the square function only takes R0 as input, right? I'm going to set R0. I'm going to set R1 equal to R0, and then we're going to multiply them together so that we effectively have R0 times R0. Okay. Remember when I hit this here, okay, it's going to destroy the old return address. Okay. So I better back it up, and that's what we're doing with the stack. And keep in mind, right, if I had changed any other value here, if I had used anything in the saved, if I used registers 9 through 12, okay, if I use those, I would also need to back them up. Okay, I'm not using them anywhere in here, so I don't actually need to back them up. But if I was, I would need to back it up on the stack as well. We'll see examples like that at another point. Okay, let's trace this. All right, let's go ahead and trace this. And you know what? I'm going to put some junk. Here, let's say this is the end of the program. I'm just going to put some stuff happening after a function call, just to kind of illustrate the point. I'm just going to add a couple things, whatever. Just do a couple, just to kind of so that we can see these things getting run. Just showing that it's going to return back from this correctly. Okay, let's trace this program. All right, step forward. Right, we're going here into the square. Okay, now keep in mind, I want to look down here, right, that we're keeping track of where we need to, when we're in the square function, and we're keeping track of the fact that when this square function returns, we need to come back up here. So that's what this return address is indicating. Okay, I'm going to continue to move forward. I'm backing up that return address in memory. Okay, and I want you to see what happens the moment I call this branch and link function. Notice the return address, the register LR, has changed. Okay, because now we did another branch and link. Okay, when this multiplication function returns, it's going to return up here, right? So it's a good thing we backed up this data for where square returns. Otherwise, it wouldn't return properly, right? It's going to actually get like an infinite recursive loop. All right, so I'm going to keep going. This is going to be kind of probably a bit long to, I'm going to put a breakpoint. Let's see if we can get it to just jump to that point there. Okay, just so, because there's some loops going on here. We see that it branches back up. Okay, back up into the square function. Okay, and oh, you know what we forgot to do? This isn't going to work right. Do you see what we forgot to do here is there's no return. Okay. So this is a mistake. It's going to run through. It's going to keep going. So it fell back into the multiplication function. We really need, we returned the, we need to take this new address and set it to the program counter. This is our return. Okay, so it's important we have that. Okay, so you saw it return. So now, right, because we returned, we backed up the original return address. We retrieved it. When it hits this line, it will come back up here and run this other stuff after it called the square function. Okay, so we can see that. I'll do that just real quick. Right. Well, since we already ran it once, let's just do this fast just to prove what's going on. We're calling the square function. Right. When we called branch and link, we got our return address here. Right. When we call branch and link again. Right. It's changed the return address. It does its thing. Right. At some point, it returns. Okay, comes back up here. Notice that when it comes back into memory, reads memory and retrieves the old return address from memory, from the stack. Okay, now it can return back up here correctly and finish the program. Okay, if I didn't do this, let me comment this out. Okay, I want you to see what happens when we return from the multiplication function. We're here, right? We're calling square. We're here, we're calling multiplication. I'm in the multiplication function. All right. Let me then skip down to that breakpoint. Okay. That's going to send us back up here. Now, I want you to notice something. This is the wrong return address. It comes up here, right? Notice it says something the runtime error, self-branching instruction detected. We never reset, right? We never retrieved the correct return address when we came back and returned from the multiplication function. So this is continuing to try to return to the same line over and over and over again. Right? It's saying LR and right. It's going and it's setting it back to the same line constantly. So it's really an infinite loop. Right? This was nice. There's a couple of nice things and bad. There's good things and bad things about this editor, this emulator. This is one of them. Is it does have some nice visual and some nice messages when some strange things happen, which I think is good from a learning perspective. Right? That kind of illustrates the point, right, of why we need to back this information up. Right, and back it up onto the stack. Okay. Now I'll just remove the breakpoints. Right, we're taking 5 and we're squaring it. Look at base 10, 25. Everything's working correctly. Okay, I'm going to stop the video there. Right, this is just not meant to give you the full-fledged breakdown on how to use all this. Right. I want you to make sure you're understanding what we're doing with stack memory, right? We're dealing with, the key thing is we want to back up, right? What needs to be preserved during a function call by pushing onto the stack. And then when we're done, we're going to retrieve everything that we backed up. Okay. If I needed to back up 2 registers here, I would make room for 8 bytes and I would put them both here with a different offset. So if I had, for instance, if I had happened to use, let's just imagine I happen to use register 9, right? Register 9 is backed up. Register 9 is backed up across a function call, right? If I use that here, I would have to do something like this. Okay, and then similarly down here, I would have to back it up. Okay, I mean, I'd have to retrieve it. The idea being that if we're using register 9, that's fine. We can go ahead and overwrite it and use it. But something else calling this function needs to know that when they're calling this function, that information is preserved. So we can go ahead and use register 9. We just have to save the original value, then use it however we want, and then we need to just return the original when we're done. Okay, we'll see more detailed examples like that at another time. All right, so thanks for watching. And if you need clarification, beautiful thing about videos is you could always go back and watch it multiple times.